Welcome to the second session. Our guest, Mr. Thiruvarul sir, from Alstom Transport India Limited, Bangalore. Welcome you, sir. Now I would like to introduce our guest, Mr. Thiruvarul sir. He is working as a component validation engineer from Alstom Transport India Limited, Bangalore. He completed B.Tech in Electrical and Electronics Engineering from NIT Trichy and ME in Powertronics and Drives from PSG College of Technology, Coimbatore. He has vast experience in the field of electrical locomotive, leading traction subsystem, component localization, qualification, validation effort, and leading European Union regional train component validation, battery charger busbar, heat sink, pump, fan and capacitor, etc. And also lead LV drives detail engineering and product certification, and solar inverter design and localization effort, and component localization and qualification testing, service upgrade projects, design, calculation, simulation, application of development, specification preparation, POM creation, electrical schematic creation, engineering change management, supporting manufacturing and production to ensure product quality and resolving daily customer site queries and issues, and also testing and commissioning of LV drives. Once again, I welcome you, sir. Now I hand over the session to Mr. Thiruvarul, sir. Please, sir. Sir, please start the session, sir. Hello, sir. So there is no audio, sir. ஆச்சு.
Hello, am I audible? Hello, hello.
Yes, sir. Audible, sir.
Okay, sir. Sorry for the interruption. There's some issue with my system and browser, so we can go back to the session.
It's okay, sir. Okay, sir. No problem, sir. Sir, please share your screen, sir. PPT.
Yes. Can everybody see my screen? Hello.
Sir, yes, sir. Yes, sir. Visible, sir.
Okay. Sir.
Okay.
Yeah. Sorry for the interruption. There is some issue with my system, so we can directly go to the session. As I said, I'm going to take a session on the power electronics technology in charging system. Mainly, I will cover on locomotive and metro section. We'll start the all the session. Most of the session, I will start with greatest scientist and human being. Quote: Excellence is a continuous process, not an accident. We stick with his words and thought process. So this is a brief introduction about Alstom. Uh, if you see the global footprint, we were almost everywhere in most of the countries. This is where we are. Uh, Most it is 36,000 plus employees, and still we are counting. More than 100 plus site across 60 countries. And this is where we are more concentrating on rolling stocks and signaling and services and systems. Hold on a second, sir, please. Yeah, I'm back. You can see here it is mainly on the rolling stocks application, and you can see it's a rolling stocks. Nothing but it is the component is running on the track, mainly on the locomotive, train, metro train, tram, and other rolling stock things. And signaling, they'll be providing like for all CBT controlled train application for a locomotive and as well as a metro sector and services post delivery. We used to do locomotive and metro train services. And system infra, we will be more. We'll be concentrating on the system infra like our metro stations and other substation erection for the locomotive, electrification, all those things. So we are the leading mobility company, including high-speed train, locomotives, and metros, e-bus, etc. And I'm very happy to announce this is the fastest train in the world. It is designed by Alstom and tested by Alstom, along with our customer channel partner Essential. It is 574.8 kilometer per hour, and till the date, the speed is not achieved by any other train manufacturer. This is a locomotive made in India concept, and we will be delivering almost like 800 locomotive, electrical locomotive to Indian Railways for dedicated freight corridor across India. So it is also one of the major design till date nobody can deliver 4,000 HP locomotive to to the market. We are the first company to deliver the high power locomotive to Indian Railways for freight cargo. It is already started application. They started pulling out the freights. So today I'm going to talk about a brief introduction about the power electronics evolution, the semiconductor devices, and the second one, how the battery charger is used in rolling stocks, which is train, either train or locomotive, or it is EMUs. Next one, how the battery charger will operate. What are the modes of operation? Next one, battery charger architecture. Here we will detail about devices and architecture. The last session will be like the most advanced development in battery charging system and as well as the traction systems. Do you have any other doubts till now? Maybe you can raise it, or else we can proceed. Is it okay to proceed? Hello. Hello.
Sir, audible, sir.
Sir, is it okay to proceed, or you have any questions till now?
Participants,
Okay,
if
I'll
I any,
proceed.
please.
Okay, I'll proceed
Okay.
then.
Yes, sir. Yes, sir. Proceed, sir.
Yeah, here we'll see the semiconductor evolution from 1960 till date. You know, a very early stage for the power conversion we used to do with the diode rectifier, and later the diode rectifier is converted into the thyristor with the control mechanism as like gate. Then later, due to some turn-off issue with the thyristor, we went with the gate of GTO. Till the date, we are using GTO-based traction converter in some of the trains. And most advanced technology in railway sector is IGBT. So currently, we are delivering the converter with IGBT technology to all the railway systems. So we'll go through what are the devices and how what is the power and voltage rating across the devices. This is a basic thing. Just want to go through where we are and where we are now. The GTO and you know the GTO technology is quite complicated, and we know it's a quite huge system compared to IGBT. Mass control thyristor. It is again we cannot use it for the higher power application. And field control thyristor. It is very limited current capacity. GO, EST, GTT. So these are the things that every devices has some limitation, and except IGBT, it has vast power voltage and power rating. And so here you can see the IGBT evolution from 1980 till 2010. Maybe it is still counting till 2020. Some of the devices, you can see the voltage rating start from 1 kilovolt till 6.5 kilovolt, and the 750 amps. Now currently we are using up to 1000 amps devices. Here you can see the inside IGBT, the chip architecture. The top portion you can see these are all the IGBT, and the bottom chips are diodes. The similar way here it is about the top portion are diodes and bottom portion are IGBT. Like this is one IGBT consisting of 6 IGBT chips and 6 diode chips. Similarly for this IGBT and this IGBT. This is for just for information, and this is the IGBT backpack module. You can see here the power connection and the gate connection here. This is a picture will explain the power rating of the semiconductor device with respect to the switching frequency. Here you can see the MOSFET which has less voltage rating and current rating, but it is a high switching frequency operated device. But this one is we cannot use for a higher power application due to the limitation, device limitation. And IGBT, it is falling somewhere middle of the chart. So it has a better switching frequency and power rating as well as the um, better operating conditions. And GTO has some limitation with device on, switch off things. Thyristor, it is a most quite old technology in converter field. Here there are key features of IGBT. Now IGBT is a fast switching device. It can operate in high switching frequency. And it is mainly on no super secure. It's better reverse lockdown safe operation region. Compared to the thermal power capacity, IGBT is better than thyristor in maybe considerable switching losses, considerable conduction losses. It's far better than thyristor or far better than GTOs. That's the same information which captured in the previous graph. So the voltage rating starts from 1.2 volt, 1.2 kilovolt till 6.5 kilovolt. And you can see where those devices are used. Maybe you can go through briefly. 1.2 volt, 1.2 kilovolt devices are used in most of the motor converter applications. 0.7 kilovolt devices are used for industrial traction application. 2.5 kilovolt device used for traction application in diesel electric locomotive. And 3.3 kilovolt, it is mainly for traction for DC catenary system. 4.5 kilovolt, again up to catenary from 2.8 to 3.3 kVA DC system. And 6.5 kilovolt device is used for mainly for 3 and 3 and 2 DC catenary system. So here we data charging system, how it will work in rolling stocks. This is the overall rolling stocks train power circuit, I can say. Top line, you can see this is a overhead line which is called as a catenary, where you can feed your locomotive. Most of the application in the Indian application, the catenary will be 25 kilovolt and 50 hertz, single phase system. And some of the very rare applications we use DC catenary, but majority of application will be 25 kilovolt DC catenary. And from catenary, the power will be collected through pantograph, which is a current collecting devices, through main circuit breaker, which will be used to protect your complete locomotive from external fault. It fed through transformer, the main transformer. It will be another line, and it feed all your traction converters. There is a traction converter, and traction converter will drive your motor, which is connected to your locomotive wheels. And where your auxiliary converter will comes, like in the locomotive for a driver cubicle, driver needs some ventilation. Some of the locomotive, it will be most luxury locomotives which will run in other countries, in uh, European countries and Switzerland, where driver needs heating ventilation system, driver needs some lighting, driver needs some maybe restroom. So for those auxiliary loads, which will be supplied by auxiliary converter inside the locomotive. This is the auxiliary converter, which will be fed DC fed auxiliary converter, which will feed all your auxiliary loads inside the train, like cooling fans, compressor, and battery charger, and motor blower, which will use to pull down your traction motors. These are the loads. Maybe we can see the further slides, different kind of accelerometers. So this is a simple pictorial representation of traction time. Here you can see this is a surge arrestor and main transformer, and this is an enclosure, and this is a horn, and this is a surge arrestor for a low voltage side. This is a circuit breaker, front end converter. These are the DC side contactor, chopper, inverter, and motor protective contactor. These are your traction motors, with sensors, speed sensors. This is our voltage and current sensing devices. Braking chopper. This is just a pictorial representation of converters and their components in the computer. Is this clear till now? Do you have any other question? Hello. Shall I proceed to next slide? Okay. Yeah. Here I will take an example of EMU architecture to explain the components where exactly it is located inside the train. EMU is nothing but electrical multiple unit. It is a classic design for our suburban train, like in Chennai and Mumbai. Most of the suburban trains are EMUs, like electrical multiple unit. And you can see the latest train, the fastest train and the luxurious train in India, Tejas Express. So, which is a train 18 concept. So, I took the train 18 concept here to explain about all the components inside the train. There you can see number of coaches are 18 coaches. So, this is why it is called train 18. Here you can see different configuration of coaches. First one is a DTC, the MC, DC, and MC, and NDC, MC, DC, like that. It is for 18 coaches. So, what do you mean DC, DTC? Which is nothing but driving trailer car. Driving trailer car. And MC is nothing but motor car. DC is nothing but trailer car. And MC is motor car. NDTC is nothing but non-driving trailer car. So it is quite similar to, it will be like repeated throughout this 18 coaches configuration. And here you can see what are the components installed in each configured coaches. For example, in DTC, battery will be installed underslung because the coaches will be occupied by passengers. So most of the components, 90% of the component, which will be installed under the train. The battery charger, which will be installed in DTC, and for a motor car, you can see the traction converter, braking chopper, and traction motors. Trailer car, which will have transformer, accelerator converter, and pantograph. And motor car again, based on the configuration and location, it will be traction converter, braking chopper, resistor, and traction motors. The classic EMU architecture, and where you can see the components located in the train. This is a power single line diagram of traction chain. So previous slide explained the pictorial representation of train components. Here you can see the single line diagram of electric locomotive traction chain. This is a catenary system and pantograph, and this is a front end. I can say it's a earthing switch. Here you can see voltage sensing devices, two DCB, and here the earthing switches again. It feed to the main transformer. Main transformer has a multiple secondary winding, which feeds the front end converter and the inverter. These are the traction converters. And here, the last one you can see, this is a HE cubicle mainly for the filter and other applications. This line will feed to the next section of the train. This is a one section. The another section will be feed from the same pantograph. It will be like a replica of the same chain. It will go for another section. Here you can see that you would say it's a front-end converter. Front-end converter, you can see this is a pre-charge contactor and main contactor, and the front-end converter rectifier. You can say this is converting your voltage to voltage of 950 volt to 1500 volt DC. And this is your inverter, which will convert your DC to AC and which fed to traction motors. The similar way, like one converter will feed to traction motors. Similar way, it is a replica of the same thing, which will feed another set of motors. So in motors, there are different kind of configuration in locomotive. We say Bobo design. Bobo is nothing but the axle. In each axle, if you see the train, some of the trains has three axle together, and some of the train has two axle together. So if you see the two axle together, the trains are called Bobo design. Bobo, Bobo, and three axle is Coco design. Each axle has one motor, which driven by uh, uh, which driven by one motor, like that, like a Bobo design and Coco design. So this locomotive is Bobo design. So each axle has one motor. So this will drive one axle. This will drive another second axle. So this is a one bogie, and this is a second bogie. So this is a complete section, first section, and similarly, there are second section which has a similar kind of architecture. So here you can see the auxiliary converter located here, which fed from DC, which will convert DC to AC, and here it will feed 415 volt auxiliary to all the loads, auxiliary loads, blower, fan, and other application, motor cooling system. So this is a EN and IEC standard for a voltage system. So what are the tolerance we can do for individual voltage levels? For example, as per IEC 50533, for all the auxiliary loads for 400 volt three-phase system, you can go up to 10% for positive side and minus 5% of negative side. And 230 volt and 110 volt. And as per IEC 60580, this is a catenary system voltage for AC 25 kV and 15 kVA, and for DC 750, 1500 and 3000 voltage. You can see here this is a nominal voltage level. For DC 750, 1500 and 3000 is a nominal voltage level. And we can see here lowest permanent voltage, lowest non-permanent voltage, highest permanent voltage, highest non-permanent voltage. So train will be designed like for nominal voltage such that it will take some most of the time, 90% of the time, it will take lowest permanent voltage, and 90% of the time it will take highest permanent voltage. But this is, you can see in representation itself, it is clearly mentioned lowest non-permanent voltage. So where the train will be relaxed for some minutes, not for continuous operation. Some minutes it can sustain and it can operate. Your complete traction system will operate on this voltage for a certain time period, not for continuous operation. So both all the component will be designed based on this voltage rating as per this standard. So till now we have covered the locomotive components and how it is the components are located inside the train. So in further slide, I'm going to explain you the battery charger operation modes. This is again it's the same slide. You can see the result of auxiliary loads, which will be necessary for a metro application. For example, metro needs a AC ventilation system, locomotive, it needs some kind of micro oven system, and lighting is the most necessity thing. And HVAC is HVAC is nothing but heat ventilation air conditioning system. It will be used for both locomotive as well as metro system. Socket in metro typical passenger needs to charge their laptop and mobile. So it will be provided through this auxiliary converter. Motor blower which will use to cool down your traction motors, which will drive your bogies. Air compressor mainly it is used for your pneumatic circuit. For example, for braking system, all the brakes are operated by pneumatic. So for air compressor, it is mainly on the emergency braking and service braking. And battery, you can see some of the control mechanism like relays and controller which will work in 110 volt DC will be provided through battery and pump based on the application. For the locomotive, the traction converter will be cooled down with a coolant, which will be run by auxiliary pump. It will be like a 415 volt three-phase pump, which will cool down your complete traction converter. So these are the modes of operation. The first one is a normal mode. I will take the classic example of Chennai Metro. How many of you seen Chennai Metro? Hello? Hello? Am I audible? Hello?
Hello. Sir, can you share your screen once again?
Yes, sir.
Yeah. Okay, sir. Now continue. It is audible now.
Okay. So I'll take a classic example of Chennai Metro. You might have seen Chennai Metro is a four-car configuration, which is designed by Alstom. So in four-car, it is a AC-fed catenary which will be taken from the overhead catenary system. So where the each car consisting of two transformer, two battery charging system. For example, the first car has pantograph, the last car has pantograph. Similarly, it's like I have explained you in previous slides, the traction time. Like you can consider this is a uh, two car configuration, two car. Similarly, another two car will be like the same architecture. So the battery charger will be located in half for a four core configuration. There are two battery chargers which will work in redundant mode. For example, some first battery charger will fail. The second battery charger will take over all the loads of car one and two. That is a scenario one. The scenario two will be like a 3 and 4 battery charger failed. The 1 and 2 the battery charger will take care of 3 and 4 accelerators. Like if both battery charger and accelerator loads are working, which is called as a normal operating mode. You might have seen in Chennai Metro, if train is passes through the tunnel, some of the lights will be switched off. It's like a power limitation mode. We save some power. Maybe during the tunnel or during the elevated corridor. So some of the lights will be switched off during the period. So where the normal mode will be like both the battery charger will be working for a four-core configuration. So train running at normal operation. Degraded mode, nothing but if one battery charger failed in four-core configuration, the other two cars accelerate loads like AC and lighting system and sockets and other emergency systems, ventilation system, everything will be fed by other battery charge. The single battery charge will take care of complete 4,000. That is degraded mode. The third one is a preconditioning mode. It's nothing but when train starts from the service bay at the morning before getting into the line. So they will do pre-checks of controller and the driver test. They will operate all the auxiliary loads. They will switch on all the loads one by one. They will check it and they will check the battery healthiness. They will check auxiliary control operation. They will check the pantograph for movement of up and down everything, and they will start the train. So some of the pre-check has to be done before getting into the line. It's called a preconditioning mode, which will be done in service line before getting to the main line. Reverse mode is nothing but, for example, if any emergency operating condition. For example, in Chennai, you might have heard in news, train was stopped in the elevated track. So by the time the passenger are evacuated with the emergency window and they were safely reached the nearest metro stations. So during those conditions, if for example, passenger is struck inside the tunnel, they will be like suffocated if trains are not operating or trains are not giving sufficient emergency ventilation fans. So in those conditions, the affected train or failed train will be pulled by other healthy train. It will, like, for example, the train one is stuck inside the tunnel, and the train two will come and it will rescue the train one, the failed train, and it will rescue and it will get the failed train to the service bay. That is called reverse mode. Store supply is nothing but when train is completed the operation at the end of the day, maybe at 11:30 will be the last train. So once it is completed the operation revenue, it will go to the service bay and they will do all kind of checks. Mainly they will check battery healthiness and battery electrode temperature and liquidity temperature and the saturation point, everything. And train will be like completely switched off. Next day morning, they will do the source supply check again, and they will do the preconditioning, and they will get back to the operation. So these are the different modes of operation of auxiliary converter. So this is a battery charger system, and this is very compact power electronics technology. You can see this is a very compact auxiliary converter. So there are two kind of auxiliary converter in locomotive application. First one is a AC fed auxiliary converter. This one is already explained to you in previous slide.
Sir, sorry.
Yes.
Is it
Yes, sir.
possible to
Yes, sir.
zoom it little bit, sir?
Uh, this is better, sir, now.
When you are, yeah, that readability is little bit. If possible, you can increase, sir. Otherwise, go ahead. No issue.
Okay. Okay. Here, this is an AC fed auxiliary system, and for example, the front end converter fed by AC, like 25 kilovolt or 15 kilovolt, which will be converted into DC. This is a DC bus and inverter portion, and it will be converted into control for the auxiliary loads. This is a circuit for medium voltage medium frequency converter, where the DC is converted into uh, step down into uh, step down into 110 volt, which is used to charge your battery. So this is an AC fed auxiliary converter, and the second one is a DC fed auxiliary converter. The DC fed is nothing but your catenary. The train main voltage will be DC. Where you can take the voltage with the inverter, and the transformer will be like an isolation transformer and rectifier, and rectifier will feed your battery. The secondary of transformer will feed your auxiliary load of 450 volt. This is architecture 1. Architecture 2, it's a quite robust architecture, I can say, where you can see multiple conversion is happening. The input contactor, this is DC precharge contactor, main contactor, input injector, and step-up chopper, medium frequency converter. Here you can see the rectifier. After it will go to the battery. After here the rectifier and inverter, then sinus filter, it will go to the main auxiliary loads. So the battery charger architecture design. So this is a classic battery charger architecture, where you can see this is a 1500 volt catenary system, where this is a front end the inverter, secondary. This is a H bridge configuration, you can see. This is a secondary side inverter. It will convert your DC to AC for the auxiliary loads. This circuit is nothing but the battery charger and auxiliary converter. I will explain in the buzzer slide. You can see this architecture. Here you can see there are 3 legs on the top side, and there are 3 legs on the bottom side. But only 2 legs are used for the inverter application. The third one is used for the prober circuit. It's nothing but to chop down your excess DC voltage during some abnormal conditions. So secondary side, it will be like normal inverter, convert rectifier, diode rectifier circuit. This complete marked portions are battery charging system, where you can see the some of the control architecture will run in 10 volt. This is a 110 volt voltage output, which will feed all your control voltage devices like relay, contactors, and some other controllers. So here you can see this is the pulsing pattern of battery charger. For example, here you can consider the QB, QC, QD. Based on the pulse width, your output voltage pattern will vary. For example, the QA, QB will be 118-degree phase shifted. Like that, QC and QD will be 118-degree phase shifted. And you can see this is the operating region of QA and QC. And you can see the voltage waveform. And further 2 or 3 cycles, your duty cycle will be increased and the pulsing pattern will be varied. And according to that, your output voltage waveform will be varied based on your duty cycle. Percentage of voltage will be increased. This is a primary transformer current. Based on your output, the pattern of the devices, the output voltage will vary, and according to that, your current will be like the current pattern will be there. So this is a operating mode of battery charger. Conventional, I would say like normal household application, the inverter, how it will work. Okay, during the main on conditions, um, the charger will be the battery charger will charge your battery to volt, and later once the power is off, it will convert your DC to the AC to your accelerator like that. This is a preconditioning mode. We would say this is a charging mode. Here you can see the constant current and the voltage will be like a charging to maximum voltage. And the second mode will be like a constant voltage mode, and like here where your voltage is reached the nominal level, but till the current capacity of the device is not current capacity of the charge is not the full level. The third one is like operating real operating mode where your battery charger will be supplying means the battery 110 volt will be converted into the 415 volt AC by the auxiliary converter. So these are the three modes of operation of battery charger. This circuit will explain about battery charger redundant mode. So as I explain you, this is a two four-car configuration train. You can take example of Chennai. Chennai has two battery charger, and one will be installed in maybe first one or two coaches, and then second will be installed in third or fourth coaches. So in redundant mode, both battery chargers are sorry in redundant mode. If the 3 and 4 coach battery charger is failed due to some issue, or it is not fed by the main catenary system, by the time the 1 and 2 battery charger will be feeding the AC 450 volt to the another battery charger via this circuit. For example, this is a main catenary. Through main catenary will convert it into the DC to AC, AC to DC, and here it is a three-phase inverter. And it will feed 1 and 2 loads, auxiliary loads, and it will feed through. It will convert the 415 volt to the 110 to charge over the battery system. A similar way, this line will feed your 3 and 4 battery charger via this contactor, and it will feed the battery of 3 and 4 coaches. Since the main catenary is not available, and it will feed through the 1 and 2 battery charging system. This is called redundant mode. This is an emergency mode where your front end converter is completely failed. Maybe you can consider the complete train. It's not fed by overhead catenary. Maybe the pantograph current collecting device it is failed. So you do not have any power inside the train. During the time, maybe the train is stuck inside the tunnel. How the train will be, passenger will be safely kept for some time till that another train will come and rescue the affected train. So during that time, if only the emergency loads will operate. For example, minimum quantity of light will be switched on, and the emergency ventilation fan to help the passenger inside the train to circulate the oxygen inside the train. So those loads will be operated with this battery. So in this particular condition, the 110 volt available battery, which will be converted by this emergency auxiliary converter to 415 volt AC, which will feed your emergency loads like for ventilation fan and maybe for lighting and other applications. For only for a few hours till this battery maybe battery time. So till then, that other train will be once the train is reached emergency mode, it will automatically give the signal to the central control station, and other train will come and rescue the train immediately. So this is the final topic. It's on the future development of battery charger and traction controller. So till then, we have seen that device is manufactured with the silicon, and Most of you cared about silicon carbide and gallium devices, which is some of the trains they already started using this silicon carbide devices for a train application. And, what is the advantage of silicon carbide and gallium devices? Mainly, it is a less power dissipation and smaller end footprint. Losses are very less compared to the silicon devices. And also, it is better performance. Like switching frequency will be much better than IGBT and normal silicon devices. Till the date we these are all the voltage rating, and it is already used in the market for some of the car industries. And this is a classic example of a silicon carbide device used in battery charging system. And this is a example. You can see in Japan they have tested train with silicon carbide traction converter. We can take this is a train, Shinkansen train is operating battery mode with the silicon carbide devices. This is another thing where you can see that traction converter is designed by silicon carbide device. It is tested successfully at Japan, Shinkansen again. You can see the train 16 car train maximum speed of 285 kilometer per hour, and all the devices are silicon carbide devices. So they have already tested this train with silicon carbide device in Japan. So that's it for today. I just covered my session. This is my contact detail for further requests. If you have any question, we can discuss for. We have some time to discuss questions. Maybe you can ask general questions, or from the PPT you can ask anything. It's open to viewers for asking the question.
Yeah, participant, if you have any questions, it's the right time to ask sir and get it clarified.
Any questions? Maybe you want to clarify any points related to railway, not only with the accelerator system. Maybe any point related to rolling stocks application.
Yeah, participant, if there is no questions, then I will. Sir, thank you. Thank you for your wonderful presentation. I hope all the participants learned a lot of things about tractions and other things. Thank you once again, sir. Thank you.
Okay, thank you all. Thanks for the opportunity. Thanks.
Thank you very much, sir.
Thank you. Thank you.